Welcome to solverfy.
We're figuring out which characteristics these algorithms have, right? And so for this first algorithm, it's a doubling algorithm, and it takes an input here, a positive integer n, so it has input. And while that n is greater than 0, which is given because it requires a positive integer, it is going to re-establish n as being equal to 2 times that number. And so imagine we picked, say, 5 positive integer. Well, we get to this step here, and 5 is greater than 0, so that checks out. And then we move here, and we're going to be setting n then equal to 10, right? But our new n, 10, is also greater than 0. So we're going to head back up here. See that it's greater than 0, head back down to the second step, and now we're going to get 20. Okay, then 20 is still larger than n, so we're going to end up doubling that again. We're going to get 40, and this is just going to keep going on and on and on and on. Okay, so despite it having this input and this perfectly defined steps, right? So it does have this definiteness. It is lacking. It's lacking an output. We never get to see what n ends up being, and it's also lacking this correctness, right? Because ideally you would just double your integer and then be done, right? So you might just say cross this off, say n is equal to 2n, and then return n would give you a more correct solution to a doubling algorithm. And due to the fact that it's incorrect, it loses its effectiveness. Being able to do that in a finite amount of time, right? Because we're just going to end up stuck in this loop here for eternity. And it's also missing generality, which is going to be missing in any incorrect algorithm. Okay, so we move on to B, and we have another one where we're just dividing here. We're given an input n. Okay, so this one has input, and each step is defined precisely, so it has this definiteness to it. And also, because we have this final step where n gets set to n minus 1, and our loop stops when n is equal to or less than 0, it is going to be finite. So it has finiteness. One thing that's lacking is output, right? So we don't have a return statement here. We're also missing correctness, right? Because n is allowed to be equal to 0, but 1 divided by 0 is not going to be defined. And due to the lack of correctness, it loses its effectiveness, right? And generality. Okay, so then we move on to 3, and we have this sum algorithm. And again, we are given an input here, this positive integer n. Okay, and each step is defined precisely, so we have our definiteness. But what we don't have is an output. We have no return statement. And we're also missing correctness, right? Because what is I and where did it come from? And we have this while I is less than 10, but then in theory we should have, I being equal to I minus something in order to get it to reduce down to being less than 10. Okay, and so that lack of correctness also causes it to lose its effectiveness. And generality here as well, if it's not performing the procedure correctly. And then we get to D. Okay, so this last one here is a choose algorithm. And so the input is 2 integers, A and B. So we have our input, It's finite, right? It just picks one or the other in one step. And it does have some generality, right? So A and B could really be anything. Doesn't necessarily have to be integers even, and this process of just choosing one or the other will apply. It doesn't have an output, right? So there's no return statement here. It also lacks this definiteness, right? So the steps are not defined precisely. It just says choose either A or B, but how are we choosing them? Are we using like a random function? Something else? Are you picking one that's greater than the other? And due to this sort of ambiguity of the one and only step, it ends up losing